We are in lesson 6 of expressions and equations. We are doing what could be any kind of algebra that we teach 6th grade through 12th grade. I've got Allie Mahboober. Allie is a 24-year-old math major from the University of Pennsylvania. She will start her 3rd year of teaching 6th and 7th grade at Harlem Central in September. She is amazing. Mahboober is now a hedge fund capitalist. He is a math major from Duke. He got burned out. He could only handle 1 year. He was amazing, but he is not teaching anymore. Right? There are 19 students in the class. It is driven. I want you to see what I mean by slides and about assembling our lessons in a way that make them accessible and shareable. I want you to see what I mean by a number string number talk, a math workshop task, and an exit ticket formative assessment. I want you to think about how the clarity of the goal started my process of having my mind blown. I'm sitting there and I hear, scholars, today we are going to, read with me, identify, create, and understand. I immediately go to my Bible, I pull out my Common Core Standards, and I'm sitting there going, where the heck did this come from? And it says, 6th grade, students will understand equivalent expressions. I'm in this world with these 2 kids who are teaching this class of 19 kids, and they realize that you can't understand if you can't create them. You can't create them if you don't identify them. I have never seen such clarity on the goal drives the quality of the lesson, because I now have kids identifying, then I have kids creating, and in the end I know they understand, right? Zaisha, can you please repeat the goal? How many middle school teachers understand to do what kindergarten and 1st grade teachers do all the time? And that is no one listens, and so they have Zaisha repeat the goal. Are you ready? Let's begin with our number strings. Boys and girls, are they equivalent? How do you know? Ready? Go. Equivalent, not equivalent. Turn and tell your partner, is 4 times 8 equivalent to 4 times the minus 3 plus 5? Yes or no? Wonderful. Go talk about how you know. Kids have all got whiteboards, right? I'm watching as kids hold up their whiteboard. I'm watching as kids sit there and go, yes, because 32 on the left, 32 on the right. Does everyone agree? No, I did it differently. 3 plus 5 is 8. They're both 4 plus 8. I don't care if it's 32. 4 times 8. It's the same. How nice. So, turn and tell your partner, what is an equivalent expression? I'm blown away. I'm blown away by a 2nd-year teacher sitting there carrying on this amazing discussion with kids. And then, click. Look at the power of animated slides. Equivalent, not equivalent. This is 6th grade. This is the first time in December the kids have ever really seen an expression, seen equivalent expressions. And they look at that and they go, yeah, they're equivalent. No, they're not. Yes, it is. Well, what do you mean? When is it equivalent? If x is 3, suppose x is 4. I mean, a. Suppose a is 4. Yeah, they're equivalent. Suppose a is 7. Suppose a is minus 5. Yeah, look at that. You don't even know that you've solved an equation. You don't even know that at this point you've recognized that they're equivalent when you solved it, when you know that A has got to be 3. And if A is anything other than 3, it's not. Oh, neat. Let's see if we can hammer that home. Every kid now is successful. Let's every kid sit saying, oh, that's so easy. They're equivalent when? And if B is not 5, they're not equivalent. Oh my goodness, I can't tell you how excited I was to sit and watch this. 7 minutes of classroom discussion that did not get resolved. Are they equivalent or are they not? You had kids say, well, of course they're equivalent because 3x and 3y is the same and you can do it this way. You had other kids saying, well, who said x is going to be the same value? Oh, how nice. And so they're not sure and all that stuff. Where there was confusion, where there was uncertainty, where kids were wrestling with, does this make sense? And sometimes we have to. I love your tweets. If you are into Twitter, go and look. I'm so honored by the things that people have picked up already. It's fun to just go sit there and see what is it that resonates and what do people quote and who retweets and all that kind of stuff. And somebody in here retweeted that notion that, duh, actually I think it said, oh boy, I have to worry a little bit less about an answer and a lot more about their thinking. Well, we let that go. All right, good. So on your mark, get set. Once again. So look at this. We sit there, we review that stuff. Let's go see about our math workshop task. Right? Look at that. Go do it. That's what we do to kids. We read it. We have them open their book. That's ridiculous. That's insane. And so what did Ali and Maboober do? Maboober then takes over the clicker and says, boys and girls, we're now doing our math workshop task. Read to me. Kids go, Jan normally rides her bike to and from work. Good. Tell me about Jan. I couldn't believe it. This is like he'd been in my workshop the day before. This is a teacher who's sitting there at 25 years of age, and he realizes that he's got to get these kids interested. And so all of a sudden, the kids are sitting there going, she's in great shape. How do you know she's in great shape? Because she's riding her bike. Well, yeah, but maybe just around the block. Oh, neat. Now maybe she's in such great shape. Oh, nice. Kid sits there and says, maybe she has a DWI. You laugh, but I think you all know. Those kids just did more inferential reasoning in 4 minutes than most times happen in an entire math class. By the way, in reading language arts, that's all they ever do. Why does reading language arts work so much better than math? Because we're forever asking kids. Why? How do you know? Can you convince me? We don't do that enough in math. Those questions are key. All right, fine. Guess what? Oh, yeah, she must be in good shape. She must be a teacher because she wouldn't be riding her bike if she could afford a car. I mean, my goodness, why can't you take the bus? The bus doesn't go to that school. All of a sudden, for the first time in their lives, the kids care about Jan and a word problem. In fact, one day, she goes to get coffee on the way to school. Yeah, she is a teacher. She needs a cup of coffee for fortitude. And then she stops at the same shop on the way home. Any questions? What kind of coffee does she drink? Right? Why does she do that? How far does that add to the trip? Funny you should ask, guys. It adds X miles to a trip each way. Now, I hope you realize that this may be the stupidest problem I've ever seen. This problem comes straight out of Engage, New York. There is nothing about this problem that has any interest or value. Except, Ali and Maboober have got all these kids sitting on the edge of their chairs wanting to do and caring and worrying about it, right? What do you notice? What do you know? How far did you go? And all that kind of stuff. And then there it is. You know that the very best lessons you've ever taught were because you asked the right question at the right time. And you know that if you teach that same lesson 3 times and you forget to ask that question 7th period, that lesson dies. You know that. And so why don't we put our lessons, our questions on our slides? Why don't we recognize that I can't punt about that? Why don't I recognize that this lesson was a gigantic success because these 2 kids spent 2 hours planning a lesson that they taught 4 times with great. Now, I want you to write and show the distance Jan travels using a diagram or a picture and 2 different but equivalent expressions. This is not a slide that they use. This is my slide that comes from the work that was then posted on their whiteboards. This is the discussion that now occurred. I want you to think about whether I'm in 6th grade, 7th grade, 8th grade, 9th grade, or 10th grade. The notion of, so what do you see? Starting with the word problem, making sense of it. Look at the different representations. Look at the idea of simplification. Look at the idea of what's going on, and look at that picture. Why is that picture so important? Oh my goodness. Come on, gang, take a trip down memory lane with me. Mathematics that needs to be banished from the face of the earth. Good morning, boys and girls. Today we are going to learn about the distributive property. Why the hell we would ever do a lesson in and of itself on the distributive property is beyond my powers of comprehension. You do know that it says in the obituary column, once again, that if I have a A on the outside and I have the quantity B plus C on the inside, you all do know, or you need to know, that the distributive property tells us that AB plus A is equal to AB plus AC. In other words, we distribute the A to the B and we distribute the A to the C. Any questions? Yeah, when was the last time any kid had the audacity to sit there and say, I don't understand that. That doesn't make sense to me. Gang, you all know that if we do not draw this rectangle, a height of A, a length of B, a length of C. What's the area of that rectangle, guys? We've been doing that since 3rd grade with multiplication. Hey, dude, it's A times B plus C. It's A times B plus C. No, it ain't. It's AB plus AC. Did it change? No. What do I have? I have equivalent representations. I have equivalent amounts. That picture makes all the difference in the world. And so look at this. Allie says to the kids, in the most dastardly question any teacher could ever do, says, oh, which one's wrong? You want to play with kids' brains? You give them 9 examples of perfectly correct work and ask them which one's wrong. Oh my goodness, they have to study every single one. I can't find what is wrong. I can't find it either. Maybe she's playing with us. Miss Allie, you playing with us? I don't know, you tell me. Which one's wrong? Where's the error? We can't find one. She smiles and she says, good work, class. Good work, scholars. Everything is right. Good. Now, which one uses the least amount of ink? What an amazing question. I don't know where that came from either. Which one uses the least amount of ink? And they all agreed it was 36 plus 2x. In other words, it's that simplified version. Where did it come from? Where did the 36 come from? Where did the 2x come from? Now go relate it to the picture. How about the picture that's going and coming? How about the picture that's the rectangle? And look what we've done. Now. Sir, you asked me before, right? Did I think that kids had learned anything after just that one lesson? And I told you, no, I didn't. I'm not sure what kids have learned at this point. I know we've done a lot of math. And so what do? I now say, given all of this stuff, look at this exit ticket. This is a much longer exit ticket than we normally do. Which of the following represent equivalent expressions? Explain or show the process. And the reason why Allie and Mabuber didn't worry back here with that last one. They didn't worry about the 3x plus 3y being resolved is because they knew where they were going. They knew what this was going to do, and they then knew. Oh my goodness. Oh my goodness. It won't surprise any of you who teach 9th grade algebra that the one that they screwed up on most was the first one. That is, the kids didn't realize that x plus x plus x plus x was 4x. They were able to fix the others. They were able to use pictures. They were able to make sense of this. They realized why each of those was wrong in a different way. Unbelievable. And so I sit there and one by one, look at this, gang. I mean, why was I so blown away? Because this came out, like a year and a half after we'd done principles of actions, and I'm sitting there going, my goodness, look at the clarity of the goal. Look at how the goal drove the tasks and the questions and the assessment. Look at the way in which they had the 3 different tasks, but that math workshop in the middle was what carried the weight of this lesson. Look at how, over and over again, there was an expectation of using representations in different ways. Look at how the lesson was driven by their questions and the discourse that emerged from those questions. Look at how this idea of fluency grew out of conceptual understanding, not shut up and memorize and distribute it properly. Understand what it means and what it looks like. Look at how the kids were expected to struggle and not always resolve it. And look at how, I missed one button, and look at how, right, in the end, I have such clear evidence that allow me to tell you whether they learned, what they didn't learn, and where to go. And so I give you an example of that only to put all of this stuff in some perspective. And now, let's do one by one really quickly. Okay? I just think that we have to agree that when it comes to these goals, first of all, Peg and Deanne and the rest of the team, there are 6 pages in here that are manna from heaven. This is PLC. I use the word PLC. This is professional learning community. This is when we sit there and say, what does NCTM say about good goals? You know that every one of those places has examples of what teachers will be doing and what students will be doing. You understand that there are 6 pages and what those 6 pages say for tasks and for representations. I can't absorb that all at once. I can barely do one every other week, but I can take those when they are appropriate and talk about what they look like, what they mean. I give you this to go play with. Okay? When you go back and worry about taking this information back to the ranch, when your middle school, when your high school department meets, when you say, we've been a little too cavalier, starting with me, with our goals, and we sort of say, well, our goal is really just, we'll do lesson 2.7. Or we'll sit there and say, today we'll solve equations. But that's not good enough. That's not a goal that gives us any direction. So I think that rarely is the goal the Common Core or the Iowa Standard Verbatim, because they're too big, they're too broad. I think you realize that that's one of the things we learned from Ali Mahuber. I think you realize that often, in one form in our planning documents, right, and it's a different form in our kids. Let me be clear about that. That the goal that I have in my teachers, in my notes, in my lesson plan, is different than the student-friendly language that I use in the class. I never say to the kids, today we are going to find the volume of right circular cylinders. I say, today we're going to figure out how much water is in Sarah's water tank or water glass. Now that's not an official goal. I think I'm cheating. Except that now has the kids interested. And I know exactly what I'm going to do, because in my lesson plan, my goal says that today students will explore the reasons why the formula for the volume works and stuff like that. Sometimes an I can statement, sometimes it should be an I will understand statement. I ask you to banish SWBAT, most of you aren't using it, and I use them as anticipatory sets. So I'm going to jump ahead just so you see this. We're going to look at a couple of lessons in a second, all right? I know I shouldn't do this, but I'm going to anyway. Right? I'm going to race through this, right? And so it's something I want to do. We're going to get to here. There's much too much to it. 3 examples of putting it all together, right? Bingo! That's not the one. There it is. There it is. Look at that. I'm sorry, but it's there. You have it. I gave you 3 sets of lesson slides. Right? And so look at this. Right? Today's goal is to classify quadrilaterals on the basis of their properties. Good. Boys and girls, will you read to me? What's the goal today? Let's go. Today's goal is to... What the hell good is this? If in fact my kids don't know what a quadrilateral is. And they don't know what a property is. So I underline those terms. And so my student-friendly goal is not straight out of my standards. My student-friendly goal is now, turn and tell your partner what's a quadrilateral. Turn and tell your partner what's a property. Give me an example of property. Give me an example of quadrilateral. What makes it a quadrilateral? So that's all I meant by racing back through this thing. That's all I meant by the first slide is just so valuable when it sits there and there we go. Right? And it is a chance to build the anticipatory set through the vocabulary. So how do you determine lesson learning goals? I mean, I adapt what's in my curriculum materials. Right? I move back and forth between the goals and the evidence. I stop and I say, wait a second, what's my goal? How will I know they can do it? Oh, neat. Well, does that change what my goal is? If this is what I really want them to do, then I have to realign my goal in that way. And then you know that the goals have got to balance skills and concepts and applications, because we've got to do all 3. There are some thoughts on goals. Peg's going to do more on that, and I'm not going to read to you from the book what you can read yourself. Cool. You know the tasks are the essence. It's the meat. Right? Find them, steal them, adapt them, revise them, reflect on them. The difference between a lesson that kids give out and a lesson that continues to be the same old are the tasks that we ask kids to engage in. You've seen I took the stupid problem with the apples and I turned it into a task. We took that ridiculous thing of Jan running to the coffee shop on her way to and from work. Right? The task gets adapted to focus on reasoning and problem solving. Tasks are the meat of instruction. Tasks are how we engage students. Tasks are how we connect it. Tasks are not mindless exercises, gang. Tasks go beyond that, and so go play. Where do we find good tasks? So here's the good news. All right? You've got, in the back of the handout, right, you turn to the very end of this particular handout and look what you've got. 2 pages that are ridiculous. 2 pages that are called Great Mathematics, Common Core Online Resources, or Where Do I Find Great Ideas for My Mathematics Lessons. So this is 3 weeks away from a June 2017 revision. Look at the top. It says www.stevemaiwan.com. This is on my website. You gotta be crazy to take this. No one copies in these things from hard copy. On my website, there is this page, and all I want to do is say to you what great teachers working collaboratively do. The 7th grade teachers, the geometry teachers, the algebra 2 teachers, the AP statistics teachers come together and say, What am I teaching? What is my goal? What are the standards? Now, where do I go to find a 3-act lesson? Where do I go to emergent math? Where do I go to see what that means and all that? And so I have given you access to great assessments, great videos, great things, and we do not have the time to go through that, but I'm here to tell you what you all know. In every one of your middle school and high school departments, there are people, some of them are you, some of them are not, who have no lives. That is, you do not have a significant other, you do not have kids, and at 2 o'clock in the morning, you are still trying to plan a lesson. You are going to Graham Fletcher's website and finding a 3-act lesson that you cannot wait to try out, while your colleagues have had to cook dinner for a spouse and 3 kids and had to go to sleep at a reasonable hour because they're older than you are, and they basically have a life. They need you. But you know what? You've got all kinds of experience that can help those crazies. When we all come together and recognize that we all can learn from each other, I depend upon the nutcases to give me all these ideas because I don't have the time to go find them. They depend upon me to say, yeah, but let's tweak it, let's change it, but wait a second, let's make this work. And so, I mean, that's just a quick and dirty set of things. There's the website, it's under publications, it's the first thing that pops up, and all I can do is tell you, great teachers steal great tasks. Done. And best of all, there's emergent math. Who has not seen emergent math? Hands. Not seen. Never seen. That's neat. That's a lot of you who've seen it. That means that every one of you during lunch ought to be able to go online, right, go find emergent math, go and look for your grade. Jeff Kroll has done us all the biggest favor in the world. He has given us amazing, amazing tasks. It's half the battle, right? How do we decide if a good task is good? You know that a good task is accessible. It's fair. It has a low entry point. You know that a good task is aligned, it's comprehensive, all that stuff. Just a chance for you to have some ideas about what we are talking about. Use representations. And so I remind you the power. You ready? Good morning, boys and girls. Welcome to 8th grade. And 9th grade and 10th grade, because we're still doing systems of equations. CD plaques are closed in a suitcase. The suitcase weighs a whopping 29 kilograms. 60 pounds? Yeah, she's got 9 pounds. 9 pairs of lead-toed shoes. Raheem packs his clothes into the same suitcase, identical suitcase. It only weighs 11 kilograms. Well, well, well. I guess Raheem is a guy. He only has 1 pair of shoes, 2 pairs of pants, and his suitcase is far less. Raheem's suitcase is, Cece's suitcase is 3 times as heavy as Raheem's. We all know we're on the ACT test. We're all on the SAT test. We are all in an application problem for a systems of equations, and we must be in algebra because it's the only place in the world that someone tells us something as stupid as and as unknowable as Cece's clothes are 3 times Raheem's. And then we ask the powerful questions that put hair on kids' chest. What is the weight of the suitcase? What is the weight of Raheem's clothes? And I'm here to remind you the way in which we teach this. Shut up, sit down, this is the way it's done. This is why I go to Desmos. This is why I go draw pictures on the board. Because I've just lost half my kids, and you know it. These kids are stupid, these kids can't do algebra. Of course they can't do algebra. You tell them, set up your variables. Sound familiar? Let S equal C's clothes. R is Raheem's clothes. X is the suitcase. Convert your variables and the sentences in the problem into number sentences. Oh good, S plus X is 29. R plus X is 11. 3 times R is equal to S. Oh my goodness. And then the best part of all, the stuff that you just love, the stuff the kids just despise. Are you ready? Let's substitute. Why? Subtract. And you know, I mean, this is what we did. And either you get it or you don't get it. And if you don't get it, it's too bad. There's nothing else I can do. What do we mean by representations? Why is it that the only way we're going to make math work for more kids is how did you do it, how did you do it, how did you see it, how did you see it? Why do we not understand that the essence of differentiation, the essence of moving from 30% to 60% and 80% of kids understanding math is alternative approaches, your way, your way, your way, and different representations. Because gang, there it is. Do you know how few classes, do you know how no textbook sits there and says this? See these clothes are 3 times Raheem's. I don't have an X, I got a box. I just know that that's Raheem, see, 3 times. What do I know about this? What's this? Come on, do it over here. What's this? Come on, there. Oh, please. What is that? That's good, that's Raheem. Good, what about Raheem? Yeah, that's his clothes and his suitcase, and altogether it's 11. Nice. How much is this? How do you know that's 11? Yeah, because it's the same thing, right? So you sit there and you go, I know that that is 11 because it's the same thing. If that's 11, how much is left of these two? That's why you subtract. It's like this is 11, so that there's 2 things that add to 18. So this one must be, and this one. So this must be 9, 9, and 9. And 2 more. And you just solved a complicated system of equations with a bar model, with a picture. That's Brave New World. That's giving kids access. And now, I sit there and I put an X over here, an X, 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 and a Y, and a Y, and I look at that picture and I go, yay, dude! X plus Y equal 11. 3x plus y equal 29. And no kid says, why do you subtract? They all sit there and go, hey, you get rid of the x and the y, and lo and behold, x plus y, you're left with 2x equal 18. That is what we mean by representations and seeing and touching, and it's been missing. And you know what? You should not feel one bit inadequate, gang. In 1989, you heard what April said. NCTM launched the standards movement. It said, and we know because the standards gods from the University of Wisconsin have told us that there is problem solving, and there is reasoning, and there are connections, and there is communication. And that is all one needs to know in terms of mathematical processes. And along comes 2000, and we rewrite the thing, and curriculum evaluation standards become standards and becomes PISM, yes, principles and standards for school, yes, principles and standards for school mathematics. Representations, where did it come from? All of a sudden in 2000 we get told, you know, there's more than just those 4. There's representations. Now, if NCTM and all those smart people didn't know that for 11 years, then, you know, we shouldn't be blamed for not knowing it either. But now we've had it out there since 2000, and now we've got representations in principles to actions, and we sit there and we realize how critical that is. And so all I want to do is say to you, go. Yell it out. Yell it out. Negative. Look at how stupid that was. Look at how stupid that was. And even in this room where you all know the answer, and I go, turn and tell your partner how much. Quietly. Good, now yell it out. Does that not blow your mind? That's again that notion of turn and tell your partner, get every kid, get validated. Your eyes, that eye, good. And then I say how much everyone says good. Ready? How many did it the right way? How many sat there and went, oh yeah, well, of course, right? To find the difference of 2 integers, I subtract the absolute value of the 2 integers, then I cite the sign. I cite the sign of the integer with the greatest absolute value. How many of you sat there and go, I know it's -4 because I have 9 and 5. I subtract them, it's 4. And I make it negative because the 9 is bigger. Hands. Good, come on, be proud. That's the rule. Mathematics is about rules. Mathematics is about memorizing those rules. It is unbelievably powerful. It'll continue to work for some small proportion of kids. And now I want to look around this room, and I want to have all you wonderful rule followers, and more importantly, the fact that almost everyone in this room is a rule breaker, to answer the question, how do you -4 if you didn't do it the right way? Come on, gang, there it is. Representations. How many of you had $5 and lost 9? How many of you sat there and said, oh my goodness, so who's the new quarterback on the Iowa State football team, or the University of Iowa? Who's the new quarterback? All right, fine, so we'll go to Tom Brady because he'll win the Super Bowl, right? They'll win the Super Bowl again. Tom Brady, 5 yards on the first play. Then they're on to him. He's sacked, loses 9 yards on the second play. What's his gain altogether? I got kids who have no idea about assigning the sign and absolute value, sitting there going, yo, dude, 5, right? Then he lost 5 and then 4 more, so he's at -4. How nice. How many of you sat there and did 5 degrees above 0, below 0? Excuse me. I'm not sure you fully understand that in every single class you have ever taught, you have at least 3 kids who cannot, will never be able to handle a horizontal number line. Their brains do not do the x-axis. Their brains do not handle up and down and start at 5 and move down. Those kids need you to recognize that the only way they will do integers for the rest of their life is above and below seawater, elevators, and temperature. I say to that kid, Tom Brady got the 5 and then lost the 9, and they look at me like I'm completely crazy. That does not get processed in their brain. I sit there and say, you woke up, it was 5 degrees on a cold winter morning above 0. During the course of the day, the cold front came through, it dropped 9 degrees. The kid says, it's -4 in the afternoon, and you sit there and go, how did you do that, Wendy? Wendy goes, well, I just moved it down 5 and then 5 more. You know that that's what we mean by representations. You know that what I'm doing now is the meanest thing I could possibly do to you. I am telling you flat out that we spend far too much time talking about an achievement gap. An achievement gap. They can't. It's their problem, it's their gap. And I have the audacity to say, as a professional, my friends, we assume the responsibility and recognize that 3/4 of the time, it is an instructional gap. Those kids care, they want to learn, they're just lost because we're not meeting them, because we are not where their brains are. We don't have to worry about this in social studies, it's just a story. Come on, gang. We don't worry about whether they know why the dinosaur ate the bug in language arts or not. We don't have the same issues. In mathematics, we have how do you make sense, what schemas do you put together to be able to do this in those ways. I got kids who sit there and go, I can't do number lines. I know I decompose the 9 into -9 and -5, -4. I've got kids that thank God I do what do you call it, the 0 pairs. I got kids who sit there, and you sit there and go, I do 0 pairs, and I go, awesome. That works for about 7 kids. What about the rest of them? And so look at the challenges we're giving ourselves. Look at how I'm forever asking kids, how else? I'm never telling kids there's one right way to do a problem. There's one right way to see it because it's just not true. Right? On the number line, I start at 5, I move to the left.